Well, greetings, mathletes, and welcome back. We're going to continue our discussion, well, our semester-long discussion on trig functions. And, in the past, what we've been doing up until now, we've been just playing with the trig functions and figuring out how to manipulate them to get particular numbers to come out. But there's been no real purpose for it. So what we're going to be taking a look at today are some of the ways that trig is used. Trig is used to find distances that you can't measure directly, right? If you're trying to figure out how far apart two ships are on the horizon, you can use trig to figure that out, but you couldn't lay out a measuring tape between them and figure it out. So that's one of the ways it gets used. And if we have time, if this video doesn't get too long, I also want to take a look at frequencies and look at wave functions. And when I say wave functions, I'm talking about things like radio waves that, because the frequency and period are two things that are very closely related. And in any case, when you listen to an FM radio, the FM stands for frequency modulation. And so if we understand a little bit about the mathematics, we can actually figure something out about the radio waves. So nonetheless, we need to go ahead and get started here so I don't ramble on forever. So here we go. Now, before we get started on solving some of the more complicated cases, I want to review. Sorry, my cat's trying to get my attention over here. It's just kind of cracking me up. Let me get back to what I was saying. I want to review just the basics of solving a triangle. So let's go ahead and take a look at an example here. So we've got them, we've got blue. Okay, yeah. So let's say this is our triangle. And let me go ahead and there we go. So we got a right triangle here. I'm going to go ahead and label the sides A, B, and C, or the angles, excuse me, and that makes the sides A, B, and C. And then we're going to give you some measurements here. So what we're going to notice is that, wow, I have that labeled wrong. Okay, so let me just tell you what I just violated. The letter always goes opposite the angle. So yeah, the capital B is the angle, lowercase b is the side. The side is the opposite side from this angle. Okay, now if we know that, say, this is 35 degrees, and we're also told that one of these sides is 10 meters, right? The goal here, when you're trying to solve a triangle, is to figure out all the sides and all the angles. Well, some of this is pretty straightforward, right? This is 90, so that means whatever this angle is has to be the complement of 35 degrees, right? So if I take 90 minus 35, that's going to give me that measurement. And that's going to end up giving me 55. So I have 55 degrees up here. So I know that angle B is 55 degrees. Okay, so I've just found that out. Now, we need to get a hold of these other sides. We have all the angles now. Angle C is 90 degrees, and then we have 35 and 55. To get this started, we only have one side. If we can find any of the other sides, then the last side can be found by the Pythagorean theorem. So that's what we're going to do. So let's see here. We have 35 degrees, and let's see here. I know that cosine of 35 would be B over C, which is the adjacent over the hypotenuse, right? Okay, so that means that cosine 35 degrees is going to be the adjacent side, which is 10, divided by the hypotenuse, which we don't know, that's C. Now, if we do a little algebra here and solve this for C, what we end up with is that C is equal to 10 over cosine 35. Now, I'm going to show you a little algebra trick that's going to save you a lot of time with proportions. Because I'm going to show you what I just did. this is the same as cosine over 1. So I'm viewing it in my head as a fraction. If I have a fraction and I need to solve, actually, let's put it this way, right? If I have something like 2/3 equals 1 over x, right? One of the things that I can do is swap the things on the diagonal. So I can put the x where the 2 is, and I can put the 2 where the x is. And you notice that brings the x out of the denominator. I could also swap the 3 and the 1, right? That's allowed as well. So although the 3 and the 1 won't be as useful, but if I swap the 2 and the x, that changes this to x over 3 is equal to 1/2, right? And then I can multiply both sides by 3 and get x is equal to 3/2. So what I ended up doing though was swapping the diagonal, and that's actually what I just did right here. I swapped the c and the cosine 35 just to save myself a little time. Now, at that point, what we need to do is just go ahead and calculate it. So okay, there's my calculator. I knew it had to be around here somewhere. So first of all, since this is in degrees, we need to make sure that we are in degree mode. Okay, so now we switched it to degree mode. Okay, so now we just need to plug in 10. Let me move this up a little bit so we can hit all the buttons. So we got 10 divided by cosine 35, and we'll go ahead and close that up. Enter, and we get 12.2, right? I'm rounding this. Your homework will tell you what to round to. So that means the side C is 12.2 meters. Okay, so we can put that in. Now, you have a few options. You could use another trig function to figure out what A is, or you could use the Pythagorean theorem, right? You have two choices. Since we've already seen using a trig function to find a side, let's go ahead and use the Pythagorean theorem just to make sure we understand it. So let's see here, Pythagorean theorem. That means that a squared, and that's what I'm looking for, plus b squared is equal to c squared. So let's plug that in. A squared plus 10 squared is equal to 12.2 squared, right? And if I go ahead and do the algebra on that real quick, A is equal to the square root of 12, my handwriting. There we go, 12.2 squared minus 10 squared. So we just need to plug that into the old calculator. Right, let's just go ahead and do that. So we need 12.2, and then we need to square it. So you have two choices here. There's a button for squaring, and then this one for your for an exponent. I'm going to use this one because it's a little neater. 12.2 squared minus 10 squared, right, is 48.84. And now we need to take the square root. So I do second function, square root. And since I don't want to type that in again, what I can do is go second function answer. And when you do that, and that's down here at the negative sign, it takes the last thing that was just spit out of the calculator, and it puts it in that spot. So if I say square root of answer, it's taking the square root of 48.84. Okay, so we get 6.98. So I'm going to go ahead, since we already rounded to one decimal place, I'm going to say A is, I just lost it, 7.0. That is a 2. Let's try it again. 7.0 meters, right? And notice that is all the sides and all the angles. Now, that 0.0 is important because it lets the reader know, whoever's reading your work, reading your paper, if you're expressing this to someone and you've done work, that 0.0 tells the reader that it was rounded to the 10th place. Right? 7.7 is the same as 7.0, but the 0.0 tells you where it was rounded. Okay, so keep that in mind. All right, so let's go ahead and take a look at the next one. We'll expand this a little bit. Okay, so let's look at a little more complicated case. So let's say this is our triangle here. Let's go ahead and do that, that, and that. Let's see here. So we'll say this is 500 meters. And let's make this, in fact, let me just draw this a little bit bigger. One more try. There we go. I'll go ahead and write this across. This is still 500. I just wanted a little more room to put in the angles. So we're going to say that this is 40 degrees and this is 25 degrees. Okay. Now, this time we're not going to be solving for the whole triangle. We're just going to be solving for part of this triangle. Notice what we have here is an altitude, because this distance right here is a right angle distance. If you turn the triangle sideways, that's an altitude. That's the height of the triangle. This is the value we're looking for right now. Now, one of the things you'll notice is that there's actually two triangles in here. I have the upper triangle, right? That's 40 degrees. This is 500, right? And I have a right angle here. And then I have the other triangle. Let's see if I can draw this one okay. Right? This is 500. That's a right angle. And this is 25 degrees. Right? So we have two triangles. And so basically what we need to do, and you're probably seeing it already, is we need to find this side and add them together, and that gives us the entire piece. Right? So we're breaking it up into two smaller triangles that we know what to do with, and then putting it back together. Right? And so it goes back to finding, this is solving a problem we already know how to solve. We've turned it into a problem we already know how to solve. So here, if I'm looking for this side, I'm going to call it, we'll call this A, and I'm just going to call this B, just so we have labels. Well, let's see, that's an opposite side and an adjacent side, so that means we're dealing with tangent. Then tangent 40 is equal to A over 500. And so A is equal to, if I cross multiply here, 500 times tangent 40. Right? Now, we can do something very similar with B. Right? B is the opposite side to the 25-degree angle, and 500 is the adjacent side. And so that means for B that tangent 25 degrees is equal to B over 500. And so this is now, if I cross multiply, 500 times tangent 25 is equal to B. And so we have both of the pieces now. So all I have to do is compute 500 times tangent 40 and 500 times tangent 25 and add those two numbers together. So let's go ahead and pull out our magic calculating box. Okay, so let's go ahead and clear this. Okay, so let's see here. We got 500 times tangent 40 degrees. And remember, we switched it to degrees already. And boom, 419.5. So this is 419.5 meters. Okay, now we need to do the same thing with tangent 25. So we have 500 times tangent 25, and I get 233.2. So that's 233.2. And now we found both of these pieces. So this is 419.5, and this piece is 233.2. And if I add those together, let's see. See if I can do this without blocking the screen. There it is. Well, it's going to block the screen. Okay. So, excuse me. So 419.5 plus 233.2. There we go. So we have 652.7. That's our total distance now. So that means x is equal to 6. Oh, God, I lost it already. That's bad. I'm becoming 652.7. I'm becoming an absent-minded professor. Right? And so 652.7 meters is the distance from one point to the next. Now, I just want to point out that you can imagine a situation where you are standing right here, right? And you have two things off in the distance you're trying to take a measurement of. You can get this distance and you can get the angles, but you can't get out there to actually measure these guys. If you can do that, you could actually figure out how far apart they are just by looking at this, just by doing this technique. There's actually other techniques we're going to learn as we go along, particularly the law of sines and the law of cosines will allow us to solve a whole bunch of stuff about triangles. Okay, so let's go ahead and take a look at the next one, right? Okay, so the next one looks like this here. And this is a slightly different situation. And we're going to stick these into actual situations once we get going here. Make sure I draw this large enough. So let's say this is our right triangle here. And we know this angle is 25 degrees. This entire angle here is 28 degrees. And what we want, let's see here, this side, we'll need this side also. We'll say that's 600 feet from one side to the next. And what I'm looking for is this distance here. I want this distance x from one point to the next, right? Well, there's a number of ways to get a hold of this. The ways that we have available to us right now, though, is pulling these two triangles apart. So we have two triangles here. Now, I could look at this little one, and this has a 3-degree angle. It's a little tiny angle. It's actually quite painful. We want to break this up into right triangles because that's what our trigonometry uses. So there's two triangles here, and they're overlapped. I have a big triangle that looks like this with 600, and this measurement is 28 degrees, right? And then I have a smaller triangle that's laid on top of it where this is 25 degrees and this is still 600, right? And so if I label this just to make this a little more clear, right? This is your big A, B, C, and in fact, let's call this D. This is the triangle ADB, right? So it's that smaller one. D would be somewhere about right there. So I just pulled that other triangle out. Well, if I know this distance, which would be the same one as this, right? Because it's overlapped, and I know the total distance from here to here, right, all the way down, I could subtract those two to get this in between piece. And so that's what I'm going to do. I'm going to find the measurement of the whole side from B to C. Then I'm going to find the measurement from B to D and subtract that off. So all I'll be left with is this piece right here, right? So that's the idea. So again, just because they're missing pieces, I'll just call this one A and I'll call this one B, just for the algebra. And I can see this again as a tangent. So here, tangent 28 is A over 600. So 600, there we go. And so from that, A is going to equal 600 tangent 28. Ay, ay, ay. It's getting too close to the edge there. Yeah. I'll make it fit. So it's 600. There we go. Tangent 28. 8. Okay. Now over here, same thing. Tangent 25 is b over 600. So b is equal to 600 tangent 25. Right? So we can figure out both of those sides now. So let's just go ahead and plug that into our calculator again. Okay, so we need, let's go ahead and clear that, 600 times tangent 28. Okay, so that's 319, and I wish I had looked at the decimal. 0.0, 319.0. And then over here, 600 tangent 25. Gives us 279.8. So that's 279.8. And remember, again, those are feet. Okay, so now that we have the two measurements, all we have to do is subtract them. We know the whole thing from B to C is 319, and then from B to D, that's the part we have that's too much. It's this amount. So if we subtract those, well, I'm just going to use the calculator. So it's 319 minus 279.8, and what I get is 39.2 feet. Right? So X is 39.2 feet. And so we just made an indirect measurement. Notice that if you're sitting here watching someone and you know their starting point, at different time periods, right, they will have moved a different, as you're looking, as if try that again. If there's something traveling this direction on here, and you know how much the angle has changed, and you know this measurement, you can use this every time to figure out how far it's traveled, right? And we're going to start looking at some of those particular details here right now. Okay, so let's go ahead and clear this off. And yeah. Okay, so let's say you're walking along a cliff by the ocean, right? You gotta, right. Why is this not working? Try that again. There we go. Right, you got a cliff, maybe a little greenery up here, some things hanging down, and here's the ocean out here, right? You're walking along around here, and you spot a ship out in the ocean. Let's make it a smokestack, right? You happen to know that this cliff is 400 feet tall, and you measure the angle. Now, we have a slight thing to talk about here. When you're talking about from your viewpoint, there's some vocabulary that goes along with it. You have your horizon, your level line, that's 0 degrees, right? If I measure an angle upwards from that, this is this is an angle of elevation, right? And then if I measure down from that, this is an angle of depression. Oh my goodness. Okay, hold on a second. My cat is going crazy again. Okay, so let's just go ahead and summarize this again now that I've taken care of my cat. So you're on a 400-foot cliff. You spot a ship out to sea what you notice is the angle of depression is 35 degrees. I know you guys always walk around on coastal cliffs with angle measuring devices, but you know. So the angle of depression is 35 degrees, and we want to figure out how far out to sea that ship is. Well, let's see here. What do we got? We have a right triangle, right? If I draw the whole thing in, I want to know what this side is. Incidentally, the ships use this too, using lighthouses, because they can identify which lighthouse they're seeing by how far the time spacing between the lights. Once they know which lighthouse they have, the height is something that is known. So they know how tall each lighthouse is, and they can figure out how far out to sea they are this way. Okay, so in any case, if that's 35 degrees, that means this side is 55 degrees. Okay, because this forms a right angle up here too. And then from that, let's see what I'm trying to find out. Let's see, from this angle, I have I'm given the adjacent side, and I need the opposite side. So once again, this is a tangent computation. So that means that tangent 55, let's scoot that down a little bit because that side is going to get in the way. Tangent 55 is going to be equal, we'll call this x, is going to be x over 400, right? So that means 400 tangent 55 is equal to x, and let's see what that comes out to. So we need 400 tangent 55. So it's 400 times tangent 55 degrees. Boom. 571 point, we'll make it 0.3. So this is 571.3 meters or feet out to sea. Sorry, the last one was meters. I was thinking this one was meters too. Okay, so just make sure I copied that right. 471.3. Yeah. Okay, so now let's complicate this a little bit. So I want to take the same idea here, and I'm going to get rid of some of this stuff. We just found out that the big X here was 571.3. Okay, so I'm going to erase the work. We now know that the full distance is 571.3. All right, let's get rid of this now that I've written it down. Right, now let's suppose, since once we found that, that I check a couple minutes later. Let's see, how do I want to draw this? We'll switch colors. That'll be better. All right, I check a couple minutes later, and the boat's moved. Right, and now the angle of depression has changed to 41 degrees. Right, so we want to know how far this guy has moved. Right, how much has he moved in that period of time? Well, we're going to do the same thing we did before. We're going to pull out the smaller triangle. And since that has an angle of depression of 41 degrees, that means its complement is 49 degrees, right? So that makes this 49, so they add up to 90. I still know this side is 400, right? And now what I need is how far out the ship is to sea right here, so I can subtract it from the other distance. So that's what I'm going to find out. I'm just going to call this A. And again, it's A over 400 is tangent 49. So that means A is equal to 400 tangent 49. So really what we're doing is we're finding this side first and subtracting it from the total to find this. Right? That's what we're doing. This piece is A. Okay, so 400 tangent 49 There we go, 400 tangent 49, and boom. So that's 460.1. Okay. So this is now 460.1. So, yeah, my handwriting. Okay. 460.1 feet. So all we have to do now is, since we know the total distance and we know this piece of it, all we have to do is subtract those two to find x. So let's see what we get. So we have 571.3 minus 460.1. Oops, I missed that. Let's try that again. 571.3. It's always a good idea to double check your entry. 460, right? 0.1. There we go. That'll be better. So 111.2. Right? So it's traveled 111.2 feet. Now, I just want to point out that if you knew the amount of time that it took, you could calculate this thing's speed just from the change in angle. Um, Trigonometry really allows you to get a hold of a lot of things that you wouldn't be able to measure otherwise. So that's one of those things that's real nice. So I just want to summarize this, okay? So let's take a look at what we had. So we started out, we had a ship out to sea, we had its angle of depression, and we had our altitude, right? How high up we were. And so what we did is we created a right triangle, since we knew those distances, and we figured out which side ratio would make a ratio, which trig ratio would make a ratio between the side we know and the side we're looking for, right? That's the thing we're trying to do. You try to make a ratio between the side you know and the side that you're looking for. You form that trig equation, and then you solve it for the side you're looking for, right? That's what you're trying to do. And that's what we did to find 571.3. Then after the ship had moved, we remeasured the angle of depression. Once we had remeasured it, we could calculate a second distance. And the difference between those two distances gave us how far the ship had traveled. Okay? All right, so let's go ahead and take a look at another deal here. Let's go ahead and get this out of here. All right. Okay, so here's our next problem. You don't get a picture for this one. And actually, oops, I'm just reading it. You only get one typo. I just spotted that. I misspelled balloon. Anyways, so we have a hot air balloon that's rising vertically. So it's going straight up in the air. And from a point on the ground, on level ground, 125 feet from a point directly under the balloon, the angle of elevation of the balloon changes from 19.2 degrees to 31.7 degrees. And we want to know how far during this time period that it changes does the balloon rise? How far does it go up when that angle of elevation changes from 19.2 to 31.7? And keep in mind that angle of elevation is from the point 125 feet away. Okay, so here's your task. See if you can draw a picture and understand the problem, and then see if you can come up with the answer. Okay, and then once you're done with that, we'll go ahead and walk through the whole problem together. So go ahead and pause it here so you can read the problem and then see what you can come up with. Okay, so let's see here. We're starting with level ground. Okay, so I got level ground. Let's see, we got a balloon rising. So, whoa, that's a funky balloon, but okay. Whatever. Looks like a light bulb. I guess it was a great idea. Okay, so there's our defunct balloon, and it's rising, right? And someone over here and I believe the problem means that someone is you, right? There's a vertical drop here. We know this distance right here is 125 feet, and the balloon changes in its angle of elevation from, let's see here, 19.2 degrees, right? And that's this small measurement here, all the way up to the big measurement, which is going to be, was it 31.7 degrees, right? And that spans this. That's the whole thing. So we have two triangles here. We have two angles, right? We have one triangle, which is the smaller one, which is 125. This is 19.2, and this side right here is this side. I'll call it B. Right? That's this triangle. Then we have the bigger triangle, which has 31.7 degrees and the same side length. And we're looking for that side, and we're just going to subtract. We're going to subtract those two measurements, A and B, once we find them. And so over here, I know that tangent 19.2 is B over 125. So B is equal to 125 tangent 19.2. I'm going to run out of room again. $19.2, and then down here A is 125 tangent 31.7, right? And so we can get those two measurements. Once we have them, we can subtract them. So let's see here. We got this guy again. Clear that off because we're on a new problem. So we have 125 times tangent 19.2 and make sure that you're still in degrees. So that's 43. Oh, I lost it. There we go. 43. We'll do 43.5 since it says to round to the nearest tenth of a degree. Or a tenth of a foot, excuse me. 43.5 feet. And then over here, we have to do the other one, tangent 125 tangent 31.7. Is 77.2, right? And so if I want, really what I'm after is the distance from here to here. How far did this thing rise? So it's going to be the difference between these two measurements, because we found this measurement and then we found this total measurement, and the difference between them will be this smaller piece here. Okay, so 77.2 minus 43.5. We'll go ahead and plug that into the magic box as well. So 33.7 33.7 feet is what it rose during this time period, right? To rise from 19.2 degrees angle of elevation to 31.7, it had to rise 33.7 feet, right? And so you can see we're getting a handle on things we can't measure directly, right? We couldn't get a measuring tape out there to measure it. I suppose we could, but it'd be an awful long measuring tape by the time we were done. And if we're talking about something that was much higher, then a measuring tape wouldn't be very feasible. So in any case, where was I? There we go. Yeah, I'm looking at the length of this, and if we go into the next thing, it's going to end up running us a bit long. So I'm going to go ahead and shove talking about frequencies and waves and things like that. I'm going to push that to the next lecture. So in any case, we have our summary of how to measure things without being able to measure them directly. And so until next time, keep your pencils and your wits sharp.